Hello, you guys. It's time for us to grade 07 Create, which is estimation procedures. The first grading we're going to do today is for Reese. So let's see what Reese has to offer us today. By clicking.
So this is Chapter 7, Estimation Procedures. Got some information here and a couple of graphs at the bottom here to fulfill this assignment. So estimation procedures estimate characteristics of large populations based on information from small samples. So that's what we're trying to do. That's what our purpose is. And we estimate population values or parameters from statistics computed from small samples and apply those to the larger population. In order to establish estimation, we have to construct these confidence intervals, which are mathematical statements that says the parameter lies within a certain interval or a range of values. And we use a couple of criteria to select that, and that is bias and efficiency. As far as bias, an estimator is unbiased if the mean or average of its sampling distribution is equal to the population value of interest. So we're looking at the average there. And then efficiency is the extent to which the sampling distribution is clustered around its average. So there we're just basically talking about dispersion. Efficiency is essentially just dispersion. So 3 steps to constructing the confidence intervals. The first one the book talked about was deciding on what risk you're willing to take, the level of risk that you're willing to take. It should include the population parameter. The probability of error alpha. The second is to picture the sampling distribution. In order to do that, we're going to divide the probability of error into equal parts above and below the mean, and then find the corresponding z-scores. And then the third is going to be to construct the actual confidence interval. So the first study I looked at, my wife is a cardiac nurse, so she helped me out with this a little bit as far as finding studies. The other ones that I've looked at throughout this course have been law enforcement or criminal justice related, and I found that really difficult to find something with estimation with regard to that. Maybe I wasn't looking in the right place, but the medical field had quite a bit more examples that I felt like we could use. So the first study we looked at.
So Reese has abandoned his criminal justice brothers and sisters and turned to the medical profession for help here. So that's just the first thing that we noticed.
Was the duration of dual antiplatelet therapy and outcome in patients with acute coronary syndrome, going percutaneous revascularization, a meta-analysis of 11 randomized trials. So the purpose of this study was to figure out and determine if antiplatelet therapy was beneficial to patients who had received coronary stents over a period of time, specifically 6 months, and then a year, and then a lifetime. And the researchers used a sample size of about 17,000 patients. Those people were collected from a total of 11 studies of individuals with acute coronary syndrome. So the confidence level was set at 95%, and this was determined using the 3-step process we talked about earlier. The researchers accepted the information obtained from the study when applied to the larger population would probably have a 5% possibility of being incorrect or wrong, I guess. And the bias was reduced using a funnel plot against odds ratio for the primary endpoint. What was learned from this study was that there was no significant difference in the duration of time with regard to the antiplatelet therapy and the patients exhibiting another acute coronary event. However, patients who stayed on the therapy for longer than a year were at a lower risk. So between 6 and 12 months wasn't a whole lot of progress, but longer than 12 months, there were lower risk issues for further acute coronary instances. So by using estimation procedures, researchers can say that the antiplatelet therapy is recommended for future patients. That would be a good thing, with a 95% success rate. And this, of course, would help medical personnel making decisions with regard to patient care. So here's the table that I loaded from the study. In the table below, the studies are listed in the right column. Those names there are the names of the studies, along with the number of ACS events in therapy over 6, 12, and longer periods of time. It's on the left-hand side. And then on the right-hand side, you can see the Z-scores, the odds ratio, and the 95%. And you can see that all of those lines there are going to fall within that 5% confidence interval on the line graph on the right. So that's my first example. The second study we looked at was coronary heart disease mortality in treated familial hypercholesterolemia. So the purpose of this study was to evaluate and show the significance of early prevention efforts to prevent coronary heart disease in patients who have a family history of high cholesterol. This study compared the results with other studies that were done prior to 1992, and that's when lipid-lowering therapy and drugs were introduced. So approximately 4,000 people were used for this sample size, and those people were taken from 21 clinics around the United Kingdom. The study used information obtained over a 36-year time period. The coronary heart disease standardized mortality ratio was compared to the population and was calculated with a 95% confidence interval. What was learned was that the significance of therapy was confirmed. However, patients with pre-existing coronary heart disease and familial hypercholesterolemia and women with the same thing may not be treated adequately. In the table below, again, our confidence interval is set at 95%. On the left side are the expected and observed symptoms. Probability of the symptom or event occurring is calculated based on the sample. So you can see over there the mortality, reasons for mortality there: coronary heart disease, stroke, accident, all cancers. So the observed incidence, the expected incidence, our confidence interval of 95%. The p-value is there as well. I went too far. The p-value is there as well, and then just kind of shows that the mortality rate is not necessarily increased or anything, but the confirmation of the previous study was basically confirmed is what it amounted to. So, so those are my two examples. It's two studies I looked at, and that's Estimation Procedures, Chapter 7. And that's it. Talk to you guys later.
So that's pretty good, Reese, and thank you for submitting that thing. Just one thing that I might notice on that, and it is it's very common. Anytime you have a large sample size, 44,000 is huge sample size, and anytime you got that, it's easy to get statistical significance because, as you know, the confidence intervals really increase owing to the smaller standard error, and that's a really good thing to have. And usually, what we do is what is the optimal sample size? Well, 100 is a good sample size to use, but some researchers contend that 30 is a perfect sample size because it doesn't, because it takes a little bit to get statistical significance. There's a host of reasons for that, too complex for this discussion. But anyway, thank you, Reese, for submitting that, and I'll see you guys on the next submission review. Bye-bye.